Okay, good evening, everyone. Welcome to O-level physics lesson on the electromagnetism. My name is Mr. Chu. Today is Tuesday, 26th of July, 2022. Okay, let's begin. As usual, whenever I start the first lesson of the topic, I'll show you the mind map of all the topics that we have learned so far. Okay, so we are now at the second last topic. Okay, we have learned that electricity start off with positive and negative charges. Then after that, we talk about current or electron that doesn't move, which is static electricity. Then we talk about current that move, charges that move, that become current. And because of current, we can form circuits. Okay, then we talk about practical electricity. Then we talk about magnetism, the last two lessons. Okay, so now we are going to link electricity and magnetism. In most cases, it doesn't make sense for us when we try to link them together. Okay, so electricity is electricity. Magnetism is magnetism. How come they are related? Okay, that's what we're going to talk about in today's topic. Okay, and then the reverse of today's topic will be the last topic. Okay, so how many of you have learned the last two topics in school already? Okay, so can you tell me if you have learned the first topic type 1, if you have learned both topic type 2? So Pei Kwan haven't learned the last topic yet, right? The rest of you, if you have learned the first topic type 1, if you have learned both topic type 2, you haven't learned these two topic type 0. Okay, thank you, Pei Kwan. Thank you, Yiting. Thank you, Oscar. Thank you, Xiao Xing. Thank you, Hao Rei. Ryan, are you at the toilet? Okay, so most of you have learned electromagnetism. Some of you have finished this, some of you are halfway. So my next question is this topic easy to understand or you'll find it difficult to understand? Okay, can you tell me from a scale of 0 to 10, electromagnetism is an easy topic to understand or is it a very hard topic to understand? Okay, if it's very hard, type 0. If it's very easy, type 10. So give me some feedback. How do you feel about this topic? Thank you, Yiting. Yiting says 7. Pei Kwan don't understand all. You are struggling, Pei Kwan, for this topic. Oh, okay, Pei Kwan think okay, right? Okay, right. Oscar, this topic are you struggling? Yeah, Ryan, you're always at the toilet. Electricity is not easy but once you get a hang of it, it's very fun because you can do a lot of things in with electricity. Okay, the rest of you, give me your feedback on this topic, magnetism. Or no topic, no feedback already. Okay, so I'm going to go through the syllabus. Okay. All right. Okay, so everybody can see we have gone through magnetism. So let me just quickly tell you what you need to know about electromagnetism. Okay, I will not use much of this, but let me go through the content. Okay, so first of all, one day, okay, so before a certain date, which I do not know when, that should be in the 19th century. Electricity is electricity, magnetism is magnetism. To most people, these two are phenomenon, and these two phenomena are not related until one day. I couldn't remember who. I think it's Maxwell. Is it Maxwell or is it Faraday? Let me see. Until one day, there's this guy called Let me see. Sorry. Hans Christian Ørsted. Okay, he actually realized that current actually produced magnetism. Okay, so in 1802, this scientist actually discovered that, okay, a current, when there's current, there is magnetism around it. Is that clear? Yeah, so before that, okay, as I told you before that, people see electricity and magnetism as separate entity. And electricity is actually not being used much at that kind of time. So when they discover charges, electricity, lightning, okay, it's actually a separate thing compared to magnetism. So it's only until 1802, these scientists discover this, but nobody actually take heed of it. Okay, never take heed of it until Ampere. Okay, Ampere discover the relationship. Yeah. Then after that, there are people like Maxwell and Faraday. Okay, all these names are famous in the scientific world. But for now, you may have heard of Ampere. Okay, you have not heard of this word before. Okay, Faraday is the unit for magnetism. Okay, and then Maxwell, if you all remember Maxwell, you all would not know Maxwell. Maxwell, there's a law that's named after him. Just like Newton's law, there's also Maxwell law. Okay, so if you're a famous scientist, you will get all the unit or the law named after you. All right. Okay, so in 1802, this guy, Ørsted, discovered that current actually produces magnetism. Okay, so that's why I put in 1802. Okay, so magnetic effect of a current means that when there's current, there will be magnetism. And because of this, there is some useful application out of it. Okay, there will be some useful application out of it. Because when there's magnetism, there is a force. Am I right to say that? Because you can attract magnetic material. Okay, so when there's a current, there is a force. Okay, so there is some application of a magnetic effect of a current. So when there is current, that is how you use electricity to generate a force. I repeat myself again. Current produces magnetism, and magnetism have magnetic forces. Clear so far? Is there such thing called electric force? Can electricity move things? Not really, right? You only can move charges like positive charge and negative charge. You cannot move your pen. You cannot move your things. Okay, whereas for magnetic force, you actually can move a magnet or a magnetic material. Okay, so current produces a magnetic effect. And a magnetic effect actually can result in a magnetic force that can move something. Okay, so from this discovery, we actually learned that current can produce magnetism that actually produce force. Understand? And when there is a force, you can make useful item. And one of the most useful item is the DC motor. You know what's a motor? Like our fan. You know our fan and turn. There's a motor inside. You put some electricity in. Because of this effect, you can make the motor turn. Okay, and therefore you will have this creation called the motor. If not for this linkage, you will not get motor. You will not get motor. You will not get car. You will not have computer. Computer inside got fan, right? Okay, you will not get a lot of things in this world. Okay, no fan, no car, okay, no computer, and so on. Okay, so this topic is a very important topic because there's a lot of real life application because of current. Is that clear? So up to here, if you are okay with the introduction of the 4 content, give me a yes reaction. Did I make my introduction clear to all of you? If it's clear, yes reaction. If it's still not clear, give me a no reaction. So at least you all can appreciate why we learn this topic. Chelsea and Harry, are you okay? Chelsea, are you there? Ryan, on your camera. Don't tell me you're always at the toilet. Okay, so let me go into the outcome that you all need to know. Okay, first of all, you need to know that what is the magnetic field due to a current in a straight wire. Okay, then of course after that you talk about solenoid. Then after that you will talk about, okay, then you need to actually know what is the magnetic effect on changing the magnitude or the direction of the current. So when the current is reversed, what happens to the magnetic field? When the current is increased or decreased, what happens to the magnetic field? Is that clear? Okay, part B, I think we have done this before. How does this magnetic effect of a current, okay, yeah, you see Ryan always in the toilet one. Okay, how you can actually use this effect in a circuit breaker. Okay, in a circuit breaker, then you need to describe experiment to show the force of a current and on a beam of a charged particle in the magnetic field, blah, blah, blah. Okay, what does this mean? Okay, what does this mean? Meaning that if you have a current in a magnetic field, okay, you will produce a force. Clear? You'll produce a force. Okay, that's what you're going to. That's what you're going to do. And all these three things are related, and we use the Fleming left-hand rule to determine. Okay, these are the things that's not easy to understand, so I want you all to listen. Can? Okay, so we do need to describe the field pattern between current in the parallel conductor and relate these forces which exist and so on. And how does a coil in a magnetic field will experience a turning effect? And how can you, and what happens if you increase the number of turns in the coil and the current? I think this the second part should be quite easy, right? The more turn, of course, will be more effect lah. More current also will get the more effect. Okay, so we're going to talk about this later on. And then because of what we have learned so far, we're going to see how you can apply to an electric motor. Okay, if not for the motor, we will not need to learn this topic. Motor is a very, very, very important and useful application in this world today. So therefore, you are learning this. Okay, then lastly, you're going to learn in a motor. Okay, we got this thing called a split ring commutator, blah, blah, blah. Okay, basically how the motor works in detail. A simple motor that's work in detail. Okay, so you're going to study how a simple motor actually works in detail. Okay, so before we continue into the notes, let me just go through the first one, A. Okay, last week I actually talked about, okay, I show you, hold on, let me on my pen. Okay, remember I told you when you want to have a current that is going into the paper they are reading, right? Okay, you either look at it like this, or you look at it like this. Okay, so let me explain to you. This is current getting out of the page. This is current going into the page. Okay, so do you all remember a dot is, why is it the dot coming out of the page and why is a cross going into the page? Can you all remember that? How to remember? Do you remember I told you all use an arrow to remember? Okay, if you remember this arrow thing, give me a yes reaction. If you don't remember, give me a no reaction. The rest of you, no reaction from you. Because there is some no reaction, I'll explain. Do you remember the arrow example that I mentioned? How to see this is coming out of the page and how do you see this going to the page? Pei Kwan, Oscar, and Xiaoxing, do you remember the arrow example? Okay, so all of you know, so I don't need to go into detail. So can you see this dot is just like the tip of an arrow coming out of the page. You're looking at the tip of the arrow. So the current is coming out of the page. And then this cross is like the end of the arrow where there's a lot of feather. Okay, so it's like going into the page. Okay, so when we see a dot, it means current coming out of the page. And when we see a cross, it means current going into the page. Is that clear? Okay, so all of you will know this. So we talk about just straight wire. So I got one dot here. It means this is a straight wire where the conventional current is coming out of the page. Whereas when you see a cross, it means there's a straight wire where the conventional current is going into the page. So you're looking at the back side of the arrow. In this case, you're looking at the front of the arrow. Okay, so what I have mentioned last week is for both of them, for current itself, you produce a magnetic effect. Clear? Okay, so the red line that I draw here is the magnetic field line. So my question is this: the magnetic field line will be turning in clockwise or anti-clockwise in both examples. Okay, do you all know how do you actually determine the magnetic field is going clockwise or anti-clockwise in these two examples? Can you actually share? Okay, Yu Ting say right hand rule. How about the rest of you? Okay, Pei Kwan also say right hand rule. Okay, so very good. Let me just explain to you. Imagine this as an arrow. Okay, imagine this arrow. This is the tip. Okay, so the current is moving upwards because the arrow is a tip. So from the top, you look down, you see a dot. Okay, so the current is a tip. So you just imagine this is the wire. You use your right hand. In this case, it's my right hand. My right hand is here. Okay, I grip my right hand, and my thumb is the direction of the conventional current. So in this example, my thumb is pointing out of the page. Pointing out of the page. Your fingers will be the direction of the magnetic field. So in this example, if I were to put my thumb pointing out of the page, imagine this is my iPad. Can you see my iPad? If I put my thumb, hard to see. Yeah, don't see. So if I put my thumb pointing out the page, my fingers will be the direction of the magnetic field line. So in the first case, if my thumb is pointing out, my fingers will be wrapping from right to left. So it will be anti-clockwise. Okay, it will be anti-clockwise. My magnetic field line will be like this. Okay, all of you know this or not? If you know this, give me a clap. If you do not know this, you need me to explain again. Please tell me now, because it's something that if you know, you know. If you don't know, you don't know. Chelsea, you okay? Okay, next one. This one is where your thumb point into the page. When your thumb point into the page, your finger will be the direction of the magnetic field line. So in this case, if I put my thumb pointing, my right thumb pointing into the page, my fingers will be moving in this direction. Is that clear? Okay, so this is the, okay, so what is the implication of this? So what did Ostad discover on that day? Ostad discovered that if I put a compass here, it will actually point towards this direction. If I put a compass here, it will point in this direction. If I put a compass here, it will point in this direction. So this is what Ostad actually discovered. When you have a current, your compass will actually point in the direction of the magnetic field line. So you put a compass, you will actually go in one round. Is that clear? So that's what happens when you have a magnetic field around a current. So you'll see that your compass will point in the direction of your magnetic field line. Is that clear? Okay, so to actually prove that, you can put your compass and then you see you'll be pointing like this. Then from there you can actually trace, okay, the magnetic field line of the magnetic field or the magnetic effect of a current. Okay, it doesn't go in one direction, it actually go in a circular manner. Is that clear? Is that clear? Okay, if you are clear, give me a thumbs up. Ryan, why are you still in toilet? On your camera. On your camera. Ryan and Xiaoxing, are you okay? Thank you, Xiaoxing. Ryan, where are you? Okay, so are you all very clear about this? Once you're very clear about this, it'll be much simpler later on. When I talk about Fleming left-hand rule, that will be more confusing. Okay, so let me just erase everything here. Okay, let me go to the notes. Okay, we are at the second last topic already, electromagnetism. Okay, so let me just go through the notes. A straight current carrying wire produces circular magnetic field line around it. And then the magnetic field is stronger at region near the wire. So if you were to draw, okay, if I were to draw, this is my current. Near it, the field line should be nearer. Then as it goes further, okay, the field line should be further apart. The magnetic effect will be near the wire. Okay, so this one is magnetic come out. The magnetic field line will be like this. Is that clear? Okay, so nearer the wire, the line should be closer. Further from the wire, the field line should be further apart. It means that the magnetic field is weaker, further away from the wire. Whereas when it's nearer to the wire, it is actually stronger. You all remember, if the field line is closer together, the magnetic field strength is stronger. Is that clear? Okay, so that is the first point. A straight current carrying wire. Okay, I can see over here. A straight carrying wire. The thumb indicate the direction of the current, and your fingers indicate the direction of a magnetic field. Okay, so you must write down the right thumb and the right fingers. So can you see over here? When it's nearer to the wire, it's closer. When it's further, it is wider apart. Okay, so these two things, are you clear about this? Okay, so the dot means the current is coming out of the paper. And the cross is like the feather of an arrow is going into the paper. So you're looking at the back side of the arrow. Okay, here you're looking at the front side of the arrow, where the arrow is shooting towards you. Okay, with a pointed tip. Understand so far? Okay, then for solenoid, we have gone through this in the previous chapter, where we are trying to create electromagnet. Do you remember that? Okay, in the electromagnet, we have gone through this before in a solenoid. So imagine, remember in the previous topic, we have a solenoid where we put maybe an iron cylinder or iron bar inside. Do you remember this? Okay, so if your current is moving this way, moving upwards, so your fingers will be pointing from the back to the front. So you use your right hand grip rule, your finger pointing to the front, then what happened? Okay, so in this case, can you see? It is going from behind to the front. So this is like your finger to the front, to the front, to the front, to the front. Okay, your north pole, your thumb will be pointing toward this side. So this will be your north pole. Okay, I think the drawing here is a bit wrong. Okay, the drawing here should be the other way around. If it's the north pole to the right, your magnetic field should be in the opposite direction. Is that clear so far? Okay, so this will be similar to what I have taught you in the previous topic. It's the same as trying to magnetize an electromagnet. Okay, the current direction will be like your fingers. Can you see down here the blue color? Blue very hard to see, right? Let me just erase everything. Okay, the current is going here. Okay, so it's coming, it's wrapping to the front. Can you see that? Or did I draw wrongly? Yeah, I think I draw correctly. Okay, then if this is your fingers, using your right hand grip rule, this side will be your north pole. This is your thumb. Your right thumb. Okay, so your current should be the opposite direction. So not current, your magnetic field line should be the opposite direction. Is that clear? How many of you think I'm wrong one? Raise your hand. Okay, so let's continue. As you can see over here, in a solenoid, the current will flow through the coil, producing a strong magnetic field. Okay, that is provided there's a rod inside. If there's no rod inside, you also still produce a magnetic field, just like there is a magnet inside the solenoid. Clear so far? Okay, so if this is the north pole, this will be the south pole. Okay, so I think this diagram is drawn wrongly. Okay, y'all hold on for a while. Okay, so I'm sorry about earlier on. The solenoid, this bend here is bending towards us. Okay, it's bending towards us. Okay, so it is in front, then behind. Then in front, then behind. Then in front, then behind. Okay, that's how. Okay, that is how the current is. So if you were to use your right fingers, were to wrap it over this solenoid, your right thumb, in this case, your right thumb will be here. Okay, this is your right thumb. Okay, and therefore this is your north pole, and this is your south pole, and then your magnetic field direction is correct now. Is that clear? Okay, so you don't need to put an iron rod inside. You can also produce a magnetic field like a magnet. But if you were to put a soft iron inside this solenoid, this magnetic field will be even stronger. Is that clear? So can you just imagine if you were to wrap your fingers, okay, around and into the page, your thumb will be pointing to the left, okay, and your thumb, okay, sorry, point to the left, right? It's not like that. You don't see your fingernail. You don't see your fingerprint. You point to the left, you'll see your fingernail. Okay, your right thumb will point to the left, and that is your north pole. Okay, I'm so sorry about earlier on. Please ignore what I said about the direction earlier. Okay, so that is the magnetic field line due to a solenoid of current. Clear so far? Okay, so let's look at this. How about for this example? You have one wire coming out and one wire going in. Can you see? Going out and going in. So it's something like this. I got one wire going out and got one wire going in. Something like this. So how do you draw the magnetic field line? Okay, we do the same thing as what you see on top here. Dot is anti-clockwise. Okay, anti-clockwise. Then cross is clockwise. All can see, right? Okay, so what happened is in between you'll get squeezed. Can you see that? So this is what happened when you put two wires together. So can you see on the right side is pointing up. On the left side of the cross is also pointing up. So everything in between will be pointing upwards. So can you see over here? Everything in between will be pointing from right to left. So are you able to draw a magnetic field pattern based on two wires like this? Is that clear? How about if you got two wires that is both pointing up? What happened? You have two wires that's both pointing up. Okay, pointing out, you get anti-clockwise, right? Then here, you'll get anti-clockwise, go down. What happened here? In between, left side is going up, right side is going down. Okay, this side is going left, this side is also going left. Am I right? So eventually, if you were to draw, okay, it's going up, going left, then going left, going down. These two will be clashing. So what happens, you'll see is you'll get something like this. Okay, where all will be turning left, at the bottom will be all going right. Is that clear? So if they are both of the wire going in the same direction, your magnetic field line look like this, like an owl. Whereas if you are on different direction, you'll all go in one direction. Okay, same thing if you do two crosses. Okay, instead of going left, you'll be going right side. Are you clear about this? Are you clear about drawing from this? Do you need to memorize how to draw all the different configuration? Or you understand and when you're given any situation, you can draw yourself. Which one? First one, you need to memorize to become number one. Second option is you understand your right hand grip rule. If you are given any situation, you're able to draw out yourself. So can you give me your feedback? Which one is you now? The first situation where you need to memorize every single one, or you use the right hand grip rule and apply. Okay, only Ryan answer me. Thank you, Eating. How about the rest of you? One or two? Okay, I hope that most of you tell me two, because I do not wish that all of you memorize every single thing. Okay, for me, who are now 18 years old, okay, I don't memorize everything. I just remember the idea and then I apply to everything rather than memorizing all the different patterns. So that's why you see I still have white hair yet. Actually have or some white hair. How about the rest of you? Do you memorize every single configuration or do you apply the right hand grip rule and then any situation thrown to you, you're able to draw? Okay, all okay, huh? Okay, next. Next. Okay, so in the solenoid, okay, this is in words, but words hard to understand. Just need to memorize that. This is like an electromagnet. You look at the current, your current is your finger, your right hand is your right hand, your right thumb is your north. You'll be able to draw the magnetic field line. Okay, like everything else, to increase the magnetic field strength, the magnetism of the solenoid or the wire. Okay, it may not be just solenoid, it can be also the wire. Okay, it can also be wire. Okay, to increase the magnetic field strength in the current or the solenoid or the wire, all you need to do is, okay, the first two apply to the wire, the last one apply to the solenoid only. Okay, very simple, don't need to memorize, it's common sense. If you increase the last two apply to solenoid, the first one apply to both the wire and solenoid. So it makes sense, right? To increase your electromagnet, you can increase your current. Number two, you can increase the number of coils, okay, in the solenoid. And finally, you can also place a soft iron core in the solenoid to improve the magnetic field strength. Okay, these three factors are you able to remember? I mean, there's no need to memorize, but does it make sense? You need to, okay, the last one, maybe you need to remember. But the first two, do you need to remember? It's common sense, right? More current, more magnetism. Correct? More number of coils, more magnetism. Does it make sense? Okay, all you need to do, just remember the third one. If you put a soft iron core inside this, your magnetic field will be also even stronger. Clear so far? Clear? Okay, so let's carry on. Okay, so we talk about the how a current can produce magnetism. We talk about single wire example. We talk about two wire example. In this case, is of two wire of different direction. I also shown you two wire of similar direction. How does the magnetic field line looks like? And finally, you look at the solenoid example. Clear? So now, how are we going to apply this idea in a circuit breaker? Okay, look at this. Okay, so what is happening here? Okay, what's happening here? Okay, you're going to study this picture first. I also don't understand what's happening here. Wow, but you can't understand, very good. Okay, for this question, I think what we need to do is you need to connect these two. Let's say this is the bulb and a battery. Okay, so we have a battery here and a bulb here. So in the case, in the whole circuit here, something goes wrong. Suddenly, there's a lot of current going through. Okay, you want to protect your bulb because if there's too much current, your bulb may burst. So suddenly, when the current becomes very strong, this electromagnet will become very strong. Your soft iron armature, okay, will be attracted to an electromagnet. So this soft iron armature, down here there's a pivot. It will be attracted to the, okay, you spring and attracted to the electromagnet. So why is attracted to the electromagnet? What happened? There is a gap here. Your current will be open. So your bulb will not light up. Your bulb will not spoil. Okay, that's what happened when the current becomes so high. Okay, so what does these two spring do? Wait, let me take a look. Okay, I understand that the left spring pull the contact away, but why would the left spring pull the contact away when the current is high? And then what does the right spring do? Yeah, look at this example, I also get a bit confused. The armature has a gap for the extended part of the contact. This one, gap for the extended part of contact. Okay, Beikwan, can you explain to us? You go and use you take over and explain to me. Okay, because I think this part I draw is not correct. Okay, so you take over here. So when the current becomes too high, this electromagnet becomes strong, then what does it attract? So the whole thing would turn anti-clockwise towards the electromagnet. Is that correct, Beikwan? Okay, so Beiguan was saying there's a pivot here. So same as what I mentioned just now. So far, no difference. There's a pivot here. So when the current is very strong, this whole thing would turn towards the electromagnet. Okay, then what happens next? So when it turn towards the electromagnet, would this wire be dragged over as well? Okay, hold on. Beiguan asked me to zoom in. Okay, so let's zoom in. So this is the pivot. So when this thing is attracted, you'll be here. Then what happened? Okay, I think I know what happened already. I think I know what happened already. Okay, let me explain. Okay, what happened is this. This soft iron armature, there's a part here that hold on to this thing here. Am I right to say that? It actually lock the contact in the place. Okay, it lock the contact in place. So there is a lock part here. Okay, can you see? This contact point here is hold in place by this armature. Okay, so what happens is when the current is too high, this armature will be pushed towards the electromagnet, and then the spring will pull the contact up. Okay, so this whole thing will be pushed up by the spring when when the soft iron armature is attracted to the electromagnet. Is that clear? Is everybody able to see that now? Oh, it took me a while. Okay, and then what happened is when it is being pulled away, when the contact is being released, the current is broken, right? Then the electromagnet will no longer be electromagnet. Okay, so let me redo again. Hold on. Okay, so what happened here is this armature hold this top contact in place. When it is too much current, it actually move forward, get attracted by the electromagnet. Then this spring will pull the contact upwards. Okay, you'll pull upwards, you'll become like this. Okay, the spring will pull it upwards. Now it is stuck on top here, beside the reset button. And then your this armature itself, okay, at first it will go towards here, you'll go towards this direction because there's attraction. But once this go up, what happened? The circuit break. The circuit becomes open. This electromagnet will no longer be an electromagnet. It will actually, then the spring will pull the electromagnet back again. At first, you will be attracted. Once there's a break, okay, you will pull it back again. This spring will pull the armature back again. But the contact is really broken. So how do you reset it? You push the button down. You pull this button down is to push this down and touch the contact, and then it can lock in place again. Then it can work again. Okay. Wow, it took Beiguan to explain to me. Well done, Beiguan. I don't know why it takes so long to understand. Okay, but do you understand now? Okay, if you all can see what I'm explaining, give me a clap. If you cannot see, give me a no reaction. All can see, Ryan and Chelsea, can you see? So how many of you actually took a while to see? Or all of you actually can see except me? But I took a while to actually see. So can you give me a feedback? Do you actually see all the while, like Bei Kwan see before me, or you actually see together with me, or you see after me? Can you give me some feedback? Hello, hello, hello. So do you see? So you think see before me, or today you are very smart, can see the direction, can see how this thing work. Can you all be my teacher instead? The rest of you, do you all see this before I see it, or you all see after I see it? No feedback. Okay, so only Yu Ting and Bei Kwan see before me. The rest of you don't want to tell me. Okay, let's continue. Okay, so this is an example of a circuit breaker where this armature actually lock this contact in place. Yeah, then when attracted away, you'll spring up, okay, and touch against the reset button. And when there's a break here, there's no more electromagnetism, there's no more magnetism, then the spring will put it back in place. So to reset, just push down the contact and then lock it back in place, and then it works again. Got it? Okay, now the next part, where we talk about Fleming left-hand rule. So everything that we do so far is all right hand. So only for this part, we use left hand. Okay, we use left hand. And how to remember this? Can you all share with me? How do your teacher actually teach you? How do you remember which finger is which one? Something that is very hard to remember, right? Okay, why is the thumb the force? How to remember the thumb is the force? How to remember that the first finger or the index finger is the magnetic field? And how to remember that the middle finger is current? Your teacher teach you how to remember why is the thumb, the left thumb is the force, the index finger is the magnetic field, and the third finger is the current. Can you share with me how does the teacher teach you? Or your teacher not teach you? You just need to memorize yourself. Okay, Hao Rui says, father, mother, child. Okay, Yu Ting say memorize yourself. So Yu Ting, now you learn that how we teacher teach father, mother, child. Do you think it's easy for you? How about the rest of you? How did the teacher teach you? How did the teacher teach you? Father, mother, child. Any other thing? Yeah, I teach you my A-level teacher how they teach us. My A-level teacher teach us FBI. Okay, I is the unit for current. I is a symbol for the unit of the current. F is force. Okay, magnetic field if you go to A-level, right, you will know that B is the symbol for magnetic field. Okay, so for me in A-level, my teacher teach me FBI. I think father, mother, child is easier, right? Okay, then when I teach in school, let me teach you what my student teach me. You want to know what my student teach me? Those who want to know one, say yes. Or type. Give me a tick reaction. Only 2% are interested to know. Okay, how my student teach me when I was a school teacher. M stands for this. C stands for this. Go and guess what F stands for. Okay, I think you all will not forget forever already, right? If you all can remember me. Okay, that is what my student teach me. Okay, this is how I remember Mr. Chu. Okay, so I hope you all can remember this. This one, I don't know what it means. I very innocent. So that's how my student remember. Okay, F, M, C. Okay, so you think it's useful, then just remember me for this. Okay, so what does this mean? What does this mean? Okay, this Fleming left-hand rule, what does it mean? It means that in an environment when there is a crossing between a current and a magnetic field. So for example, you have a current moving this way. And then you have a magnetic field that is at least not 0 degree to the current. Okay, this is your current. This is your magnetic field. When you have a current and a magnetic field intercrossing together, it will result in a force. Okay, it will result in a force. So it's a very powerful concept because I can put a north pole of a magnet here and a south pole of a magnet here, and I put a current in between. This wire will move. Okay, this wire will move either out or into the page. So let's imagine the current is moving from left to right. Okay, of this screen. The magnetic field is moving from down to up. Okay, so you take out your left hand rule. Your C is moving from left to right. Your M is moving from down to up. Then you realize that your left thumb will be pointing towards you. So what happens is, if you put a current between the magnet like this wire will actually move towards you. Is that clear? Okay, is that clear? Get it? And this actually is a very useful application, and therefore you can produce a thing called motor. So I repeat, if your current is in a 90 degree to the magnetic field, it will actually result in a force that is 90 degree to the direction of the current and the magnetic field. And in this case, you'll be moving out of the page towards you. Okay, if you use the Fleming left-hand rule, you know, F is the true, right? Okay, M is your magnetic field. You point it from down to up. Your current point from left to right. Your thumb will be pointing towards you. So the wire will actually move out of the page towards you. Everybody understand this? The Fleming left-hand rule? If you understand this very well, give me a yes reaction. Okay, because this is something that a lot of students, they don't understand, and they give up. Then this topic becomes very difficult. Chelsea and Ryan today, the reaction very slow. What happened to both of you? In the toilet again. Mr. Ryan. Ken? You got it? Does your school teacher give you enough example to practice? Are you clear about this? So now today, some of you learn. This is father, mother, child. Then you also learn a new one. F, Mr. Chu. Okay, so I think you can remember this forever. But the important thing, it must be left hand, not right hand. Right hand will be another thing altogether. If you use right hand, it'll be totally wrong. Okay, for this example, you have to use the left hand rule. Okay, a lot of things we use right hand earlier on. So in this example, you must remember is the left hand. That's the thing I need you all to remember. Okay, the MC, I think by now all of you shouldn't forget in your lifetime. If you remember me. Okay, you forget about me, of course you'll forget. Then you just remember father, mother, child. Or you can remember FBI. Okay, FBI. Let me show you all another example. Why is it called B? Remember this diagram I showed you earlier on? Can you see I is the unit for current? Okay, B is the magnetic field. Okay, can you see here? Magnetic field, the short form is B. You will learn this in A level if you go to JC, or you go to poly or go to university. You're going to learn deeper, right? Magnetic field is represent B. Okay, therefore your index finger can be represented as B. Okay, so my A level teacher teach me as FBI. Can? Okay, so but to remember FBI, you must understand that magnetic field the short form for magnetic field is B. Okay, the short form for current is I. Okay, for I. And the short form for force is F. Okay, so if you remember the short form for the three things, just remember FBI. You all know what's FBI now? Do you know what does FBI stand for? And why it become an easy thing to remember? FBI is like the secretive service in the USA where they do detective work. Okay, so that's how they use this to remember, to help us to remember. Okay, so if you go to JC, okay, teacher may teach you FBI because B represent magnetic field, I represent current, and then F represent force. Then you all know FBI is something that is easy to remember. I do not know at your age, do you all know about FBI or not? Or is it something that only my age people know? Can you give me some reaction or some feedback? Do you all know what's FBI in the first place? Do you all watch movie? Do you all know what's FBI? Tell me yes or no. Type it out. Because I want to know whether does it still relevant to you? Ryan, why you laugh again? You like to laugh, are you? Okay, so do you all know what's FBI? Because I don't know, I'm not entirely sure whether you all know. Okay, so in JC you'll learn FBI. It'll be easy to remember because F is the symbol for force, B is the symbol for magnetic field, and I is the symbol for current. Earlier on I mentioned unit, right? I'm wrong. I is the symbol for current, not the symbol for the unit. Okay, so it's very easy, FBI. Okay, but my students don't like FBI. They still prefer F, Mr. Chu. Okay, let's continue. Okay, let's continue. Okay, so this one I mentioned just now. If you have two current in opposite direction, okay, based on your right hand rule, you can be able to draw the magnetic field of this pattern. Is that clear? Same thing, if it's on the same direction, you can see you wrap around it in this manner. When you wrap around it, it seems you actually like trying to close them together. So these two wires will move together. Alright, in this case, can you see all will squeeze in between? So the wire actually will move away. Can you see from the magnetic field line? Can you see that why these two wires will move away? And then from this pattern, when you try to close it in one circle, these two wires will try to move toward each other. Can all of you see that? If you can, give me a yes reaction. If you cannot, give me a no reaction. Ray and Bei Kwan, can you all see? Okay, can you all remove your remove all your reaction? Remove all your reaction now. Remove everything. Remove. Ryan, Bei Kwan, remove your reaction. Okay, Bei Kwan, remove your reaction. Okay, so can you all see based on this diagram? Can you all see that? Can you all see that? Because everything is squeezed inside, so the wire will move away. And in this case, it's moving in circle, it's trying to wrap around the two wires. So the two wires come together. Can you, if you all can see, give me a yes reaction. If you cannot see, give me a no reaction. Bei Kwan, Xiaoxing, are you okay? Okay, next. Now, for this example, before I go into the motto, for this example, we use the Fleming left-hand rule. Okay, FBI or F Mr. Chu or Father, Mother, Child, up to you. Okay, which one that can help you remember the best? Just remember that. Okay, in this case, can you see when we see cross, 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 what does it mean? Okay, cross, cross, cross is just the same thing. Cross, cross, cross is like going into the page. Okay, your current is your middle finger. You move from left to right. Okay, then the magnetic field is going into the page. You use your index finger and point into the computer. Okay, your current, your middle finger, move from left to right. Okay, then you realize that your thumb will be pointing up or down. Okay, your thumb will be pointing up or down. Okay, your thumb will be pointing upwards. So when the positive charge is moving from left to right into a magnetic field that's going into the page, you have an upward motion. Okay, is that clear? So direction of current is always based on positive charge. Okay, if it's negative charge like this, you just assume that the current is moving in the opposite direction. The conventional current is moving in the opposite direction. So in this case, your current is from right to left. Your index finger, your magnetic field is into the page. And then you'll realize that, okay, use your left hand, your current is moving from right to left. Your magnetic field is into the page. Your thumb is moving downwards. Therefore, your negative charge, okay, just imagine it's moving from right to left. So your force will be going down. So therefore, as the negative charge move from left to right, just assume that the positive charge moving from right to left, it will give you a downward force going down. Okay, I know this sounds very funny, but anything you see negative is just opposite of it. So this negative charge moving from left to right, you just think that the conventional current is moving from right to left. So your middle finger or your C finger, which is your middle finger, should be pointing from right to left. Okay, clear all your reaction. If you understand the right side here, dealing with the negative charge or the electron, if you understand perfectly, give me a thumbs up. Okay, give me a thumbs up. Okay, thank you everyone. Okay, so we have gone through the very basics of electromagnetism. Basically, the whole topic that I talked to you about today so far is two things. Number one, a current will produce a magnetic field. Okay, number one. Number two, a current in a magnetic field will produce a force. Is that clear? Okay, so for example, this is a conventional current moving from left to right. Okay, so basically, every current will have a magnetic field around it. Is that clear? So the magnetic field reacting with the magnetic field here, if they are in opposite direction or they are in perpendicular direction, it will always produce a force. So the first concept that we learn in this topic is number one. The first concept is current produce a magnetic effect. That's the very first big idea you all must know. The second big idea you all need to know is, if you put a current that is perpendicular in a magnetic field, it will produce a force that is perpendicular to both the current and magnetic field. And to determine the direction of the force, you use the left-hand rule, not the right-hand rule. Okay, that's the second big concept you all must know. Are you all clear about this? I'm just wrapping up the whole topic for you all. First concept you all need to know is current produce magnetic field. Okay, so this current produce magnetic field. Can you see? This current produce magnetic field. It will be like this. Clear? It will be like this, like this, like this. And then you're in a magnetic field area. Okay, you have a magnetic field in this area. So can you see? At the bottom of this, at the bottom, can you see they are all in the same direction? At the top is in different direction. So can you see that at the bottom, they will have more lines. On top, they will cancel each other. So when there's more line below and on top, they will cancel each other, it will result in this current going up. Can you all see this? I know it's hard to see in a 2D diagram. But when I draw like this, can you see why there's a force that's going up? At the bottom, can you see here at the bottom? Okay, wait, let me draw again. So this is the current. Okay, the current pointing out the current is pointing out of the page. Okay, so the magnetic field line will be this way. Do you agree? Do you agree? Then, if you put it in a field line that is from left to right. Okay, you are from left to right. Okay, can you see that? Can you all see that at the bottom, they are all in the same direction? So they are all together. At the top, can you see they'll cancel each other? So the resulting is like this. When you have current in the magnetic field, you will have this kind of effect. Okay, then on top, there'll be nothing much. Okay, there'll be nothing much. All will squeeze below. Okay, when you see this sort of effect, can you imagine that this magnetic field will push the wire up, and therefore the force is going up? So if you forget your left-hand rule, you draw this out, then you can see what's the direction of the force. Okay, because on top there's nothing, they cancel out. So on top there's nothing. On bottom there's all pointing to the right. Okay, so everything point to the right. What happens is you'll go up. Because there's a lot of lines below, there's less line on top. The result will be this thing will go up. Is that clear? Can you see now? If you can see, give me a clap. Ryan and Chelsea, again, two of you, where are you? Why the two of you today we are so slow? Ryan still in the toilet. Okay, so let me repeat myself one last time. The first idea you must know is current produces magnetic field. Number one. Okay, current produces magnetic field. And because current produces magnetic field, when it is in perpendicular to a magnetic field, they will react and there will be a resultant force. Okay, I already drawn for you this example. The resultant force is going up because there will be a lot of magnetic field line below. There will be no magnetic field line on top. So it will give an effect of an upward force. You all can see that? Okay, so this is the second big concept that you all must know. So after knowing this concept, can we create something useful for this world? Okay, magnetic field can be produced with magnet. Current can be produced with electricity. So the idea is like this. With magnet and electric supply, when you put these two together, we can make things move. You understand this idea? Okay, with a magnet and electricity, we put them together in the correct direction, we can result in some movement. Okay, that is the implication, that's the reason why you learn this topic. Okay, because you can use magnet to create magnetic field, and we know that there are electricity around us, and if we bring them together, we can make things move. Get it? And then we're going to go into the last part of today, which is the application of why we learn all these things. Yeah? It's because you want to make things move, we will result in this thing called a motor. Okay, or this last part of today. Are you clear about this? Can you appreciate why we learn this topic now? If you can appreciate, give me a thumbs up. Pei Kuan and Chelsea, are you okay? Okay, so let me explain in detail about how to make things move. Okay, how to make things move. Okay, the idea here will be, remember I told you, Fleming left-hand rule. If there's a magnet, if there is a magnetic field plus a current, it will result in a force. Okay, you get it? You result in a force. Okay, first of all, can you see the north and south pole? Okay, there's a north and south pole. Okay, we talk about the magnetic field here, the north and south pole. Okay, the magnetic field is over here. Let me use red as an example. Okay, you have magnetic field line going from left to right. Okay, let me make it bigger. Let me make it bigger. Okay, so just now I mentioned, if I have a magnetic field B plus, okay, a current, I use blue, okay, it will result in a force. Okay, so let's look at this. Let's look at this. We just look at A to B. Okay, we look at A to B. Let me highlight to you. Just look at A to B. Can all of you use your magnetic? Can all of you use your left hand rule? Your middle finger, the current is moving from A to B. Your middle finger points from A to B. Can all of you do that? Then north to south, right? I just draw one line. Okay, so your index finger will be pointing from left to right. Okay, so all of you do that now. A to B is your middle finger. Your index left finger is from north to south. So can you tell me, based on these two interactions, your force is going up or down? Type it out in the chat. All of you do that now. Okay, your force will be going up or down. Let me try myself also. Magnetic field, left to right, current. Okay, Yiting, correct. How about the rest of you? Does your force go up or down? Yiting, correct. Hao Rui, correct. Ryan, you try again. Use your left hand. Left hand, your three fingers, all 90 degrees perpendicular to each other. Your index finger is the red color line. The yellow color line is your middle finger. Then your thumb is pointing up or down. Okay, Ryan, you try that again. Okay, this red color line is the red color line is your middle finger. Your yellow color line is your, sorry, I'm sorry again. The red color line is your index finger. The yellow highlighted line is your middle finger. Then your thumb is pointing up or down. Your thumb is pointing up or down. Okay, this is your left index. This is your left middle. Okay, and therefore your force is your left thumb. Remember FBI? Okay, FBI, your thumb, your index finger, and your middle finger. Okay, Ryan, Chelsea, are you able to do that? How about the rest of you? So at this point, where the yellow and the red intersect, does the force go up or go down? Okay, so far, Ryan, Chelsea, Hao Rui, Yiting are correct. How about Oscar? Oscar and Bei Kuan? At this point, this intersection, okay, this intersection, does the force go up or go down? All of you try. The red line is your left index finger. The highlighted yellow line is your left middle finger. So your thumb will be your left thumb will be pointing up or down. Oscar and Bei Kuan, can you give me your answer? Okay, Oscar, well done. Bei Kuan, are you there? Okay, so all of you agree, the same direction. I'm only left with Bei Kuan. Bei Kuan, are you there? Are you struggling? If you need help, I help. Can you tell me your thumb will be pointing up or down? Bei Kuan, are you there? Why are you not listening again, Bei Kuan? I want you to watch this whole video one more time. The magnetic field is from left to right, represented by the red color line. So let your red color line be your left index finger. The current is moving from A to B. Okay, so let your left middle finger be your A to B. Okay, so your index finger is left to right. Your middle finger is from A to B. Then your resulting force is your thumb, your left thumb. So the force will be going upwards or going downwards. Okay, so very good. So all of you agree you have a downward force. Is that clear? Now we do that to the next the other side, C and D. Okay, can you all do the same thing? Your current is moving from C to D. Your magnetic field is from north to south. The force will be going up or down. Okay, all of you go and try using your left hand rule. Really go and try. Okay, well done, Yuting. How about the rest of you? Well done, Hao Rei. The rest of you? Well done, Ryan. Any more? Qiao Xing, Bei Kuan, and Oscar. So on the right side here, this intersection will result in an upward force or a downward force. Oscar, well done. Qiao Xing, well done. He left with Bei Kuan. Hey, Kwan, are you there? Is it up or down? Don't give me thumbs up there. Up or down? Okay, very good. So do you agree that on the right side, it will result in a upward force? Clear so far? Okay, so this whole thing will rotate in this angle. Can you see that? It will rotate in this direction, which is anti-clockwise. So are you able to actually see that? Are all of you able to see that? Yes or no? Okay, y'all can see that, give me a thumbs up. Okay, based on your left hand rule that you understand, on the left side here, on the right side here, it will result in this thing turning anti-clockwise. If you can see that now, give me thumbs up. Ryan, Bei Kuan, can you see? Thank you, Bei Kuan. Ryan, are you there? Okay, very good. Ryan, are you there? Are you there? I'm going to end the lesson already. Are you there? So Ryan, can you see why this coin will turn anti-clockwise? Okay. Before I talk about the first point and the second point, all of you can see how this thing works, right? So as this thing keep on turning, does it look like a motor to you? Does it look like a motor to you? Like an end of a fan? So just turn. Can you see that? Okay, so this is an example of a fan. How you can use electricity and the magnetism to actually move things. In this case, we try to rotate things, and that's how a motor works. That's how a fan works. You can help things rotate. Okay. Are you able to appreciate this? Appreciate this? Can? Now, before I go through these 2 points, to make the force stronger, okay, this is the turning effect of force. Okay, to make your force stronger. Okay, this actually is turning effect. But can you see why is it turning effect? Because there is 2 forces. Okay, there are 2 forces away from the center. So it creates a turning effect. To increase the turning effect of the force, okay, what can we do? What can we do? Okay, okay, can you see down here? this is one coil. Can you see? This is one coil. If we increase this to 10 coil, the turning effect will be stronger. Can you see that? This is one coil, it's only one round. So if we increase this coil to many coil, it'll be actually stronger. Number two, okay, inside this coil, we insert a soft iron core. Okay, how else can we increase the force, the turning effect of the force? We increase the current. Can you see that? We increase the current. And lastly, we can increase the magnet, the strength of the magnet. Okay, so the last 2 points is common sense. I'm sure you all don't need to memorize. Okay, what you need to understand is, if I put the iron core inside here, you also increase the force. Number two, instead of one coil, we do many coil, you also will increase the turning effect. Is that clear? Because one coil, one wire, okay, one wire, it will produce maybe less magnetic field. You have a lot of wire. You have a lot of wire, it's just like increasing the current. Am I right to say that? It's just like increasing the current. We will have the effect will be much stronger. Clear so far? Okay, so you all understand the whole idea already? Then I talk about the last 2 points. Could you understand how having current and magnetic field will cause this thing to turn? And when you turn, you're creating a motor. And then why we talk about DC motor? Because this power supply is DC power supply. Okay, it's not alternating current, it's DC power supply. So the current only flow in one direction. Okay, therefore it is called a DC motor. It results in the thing, the Q, the PQ, turning anti-clockwise, turn round and round and round. Okay, that is your motor here. Your PQ is your motor. Okay, the motor that causes the fan to turn. Okay, so now we're going to talk about something. For this to continuously turn in the same direction, okay, in the same direction, anti-clockwise direction, your AB must always be, the current must always be from A to B. And then your CD, your current must always be from C to D. Are you clear about this? Okay, so for it to forever turn in anti-clockwise direction, the current on the left side must always from A to B. The current on the right side must always be on C to D. If this circular thing, okay, if the left side is connected to the left side, the X, forever, as the A turn to the right side, the current will be from down to up. Then it will not work already. You'll be turning it left, turn right, turn left, turn right. Can you imagine? It's like pendulum. Turn one round, turn back, turn one round, turn back. Okay, so what you need to do is this coil must be connected to this thing called a split ring. Okay, there's no current going through this. So when the coil is at the left side, okay, the left half of this circuit, the current will always be from A to B. Okay, so when you turn, the CD turn over to the left side, you'll be touching the X. You'll always be from A to B. Understand so far? Okay, do you understand so far? Why this communicator is for? Why is there a split? So that whenever the right side flip to the left side, the current will always be from A to B. Likewise, from the left side flip to the right side, the current will always be from C to D, because current is going into this thing, into the battery. Then battery come out. Is that clear? Can you see that inside the current, this is the current always going this direction. This current is going this direction. Clear? So on the right side, the current is always flowing from C to D. On the left side, the current is always flowing from A to B. So you need to have a split ring communicator so that whenever it turns to the left side, the current is always left from A to B. And then when the wire is on the right side, the current is always from C to D. Can you appreciate this now? Why we need this thing called the split ring communicator? Okay, you all understand the split ring communicator very well. give me a clap. Okay, if you understand the split ring communicator, well, give me a clap. Okay, very good. So can you look at this thing here? Now we're going to talk about the last one before we end. Okay, can you all see this? So now can you see this coil will always turn in anti-clockwise. So this split ring communicator will always continue to turn in anti-clockwise as well. Understand? Can you all see? This split ring communicator will always turn in anti-clockwise as well. It will be always turning. Clear? So when it's on the left side, touching the X, current move from A to B. On the right side, touching Y, you'll be current moving from C to D. So what happens is this, okay? This thing X and Y, okay, X and Y, is like a carbon brush. Means that your wire touch this, carbon, okay, carbon is actually electrical conductor. Okay, even though it's a non-metal, carbon is an electrical conductor. So this X and Y are a metal conductor, but it's very soft. So it's always touching part of the communicator. Okay, so these X and Y are the carbon brush that ensure that the wire, okay, is always in contact with the communicator. Are you clear about this? Okay, do you understand? Do you understand this carbon brush? What is it for? Okay, if you understand, give me a yes reaction. Hey, Kwan, are you there? Hey, why the assistant disappear? Very funny, man. I still see the assistant here. Hello. Okay. Now, if you are clear about this topic, okay, give me a clap. Then I'll give you all the exit question, and then you all may go. Okay. Since all of you have learned this topic in school already, after going through just 1.5 hours with me, how much have I value add to you today in understanding this topic? 1 being no value add at all, 10 being I value add very much. Okay, give me a rating and tell me one thing you learned today. Once I call your name, you may go. Okay, tell me how much have I value add to you in this topic, and tell me one thing you learned today. Okay, to be a bit more specific, type a bit more than one sentence. Once I call your name, you may go. Okay, Ryan, you may go. Ting, you may go. Oscar, you may go. Chelsea, you may go. Okay, Hao Rui and Bei Guan. Left the 2 of you. Okay, thank you everyone for being here today. Thank you, thank you.